that sort of doesn't quite square off. So there's something that I haven't said yet that makes these two not as opposing as they seem initially. Okay. So now that's why I first want to talk to you a little bit about the Calderon problem. This has an early history starting. So this started in the early 80s. And the last result that sort of, I mean, there are still results coming out, but I would say the last result that sort of was a significant advance is from 2006. And I'll now describe these results in some generality. Okay. So actually, maybe could we do that just for 5 minutes? Could we raise the screen there? Because then I'm going to use the blackboard over here. Great, okay. And I'll just use one blackboard. Yeah. Sorry for being That's fine. Okay. Well, but I will use it here. So let me do the following thing. So I'm going to use it the case where A and B are what I would call isotropic. So what does it mean that A and B are isotropic? It means that A and B are really A is equal to a scalar times the identity. So it's a matrix, but it's really a scalar. And B is equal to, of course, the same as scalar times the identity. So it really means that because for this equation, you could have a positive definite matrix, right? You can have this to be a positive definite matrix. That's typically how elliptic operators are. But the ones that have a matrix in there, they're called anisotropic. And anisotropic means that the material, so this is as opposed to sort of A and capital B, which may have, is anisotropic if they have, so I would say, wait. So I would say, let me say, A is anisotropic if it has different eigenvalues.
Trên được để chắc mấy lần.
Because, I mean, if it has different eigenvalues, then you could still maybe diagonalize it. But if it has different eigenvalues, then the two diagonal entries are not the same, and so it's not a scalar times the identity. It's typically a medium that you could sort of have, let's say you had sort of what you call resistors in parallel and resistors in series. You would have a conductivity across here, which is different from the conductivity in that direction. So the conductivities could be wildly different in different directions. That's what I call anisotropic. And when it's isotropic, that means that the material conducts the same in all directions. You cannot tell directions. It's directional independent at any one point. And this makes a whole lot of difference for the Calderon problem. So actually, Calderon problem is not really this. It says, is it true that if A and B are isotropic, then this thing here. This is really what I should have, in all fairness, because that's how Calderon formulated, and otherwise it would be trivially not true. So the Calderon problem, is it true that if A and B are isotropic, then this is true? Then if they have the same period tetranomen they come out, then A is equal to B. Now this is actually fairly close to having been proven. So I will give you the result for the, so let me just state some results. So there were results sort of in 84, 85, and those results were by, Cohn, and myself, which proved that if you have isotropic and piecewise analytic, piecewise real analytic, so I would call this piecewise analytic, and this is in the sense of given by a germ, so real analytic. So if A and B are real, piecewise analytic and isotropic, then lambda A is equal to lambda B implies A is equal to B. That's a result from 8485 that appeared in the communication through an apply. Then there is actually 1987. There's a result by Ullman and Sylvester. So this first thing was by Bob Coleman and myself. Then there's a result, a very, very deep result from sort of a fundamental result from 87 by Ullman and Sylvester that says if you can go from this piecewise analytic category, you can make the step that says if A and B are C infinity. So you can take the leap from not being given by a germ counted being any coefficients, but actually being just a C infinity function. And if A and B are C infinity and isotropic, and n is greater than or equal to 3, and I haven't told you what n is, but n is always a dimension. So if you are in dimension 3 and higher, if you are isotropic and if you are C infinity, then it's true that lambda A is equal to lambda B implies A is equal to B. This is a result from 1987 that appeared in the Annals. Okay. So now you can say, that doesn't do everything. Then actually in that spirit, well, let's go down here and I'll tell you other results. Then actually, so you can see there's one thing here is who knows what happens in 2-dimension. 2-dimension is slightly tighter, and I don't have the time to show you why 2-dimension is slightly tighter, but the problem is slightly more difficult in 2-dimension. So there is a result that from 1996 by Adrian Nachman. And this also appeared in the Annals that says if n is equal to 2 and A and B are C infinity, then and isotropic, then a lambda A is equal to lambda B implies A is equal to B. It's also true. So now you have sort of the 2-dimensional result, at least in the C infinity category. Well, now once someone has proven, so the first result by Bob and me were in the analytic category, there's not really, you can't really carry the analytic category that much further, but once someone has done it in C infinity, you can be sure that there's someone who will cut off the regularity. So basically the regularity was then over a number of years, taken down to basically C2. And there's a good reason, or C11, there's a good reason that you need one derivative. I don't have the time to tell you that, but there's a very good reason. So this result was cut down to, I'm not the expert on that, but let's say C2 to be on the safe side. And this thing here was certainly taken down to C2. I think it was actually taken down to C1 alpha for alpha sufficient large. But that's not really the point. These techniques could be used to do that. Now there was a result, which is sort of another fundamental result in 2006 by Astala and Eichhorn. And this also appeared in the Annals, that says if you are in 2-dimension, so for n is equal to 2, and A and B are in L infinity, and this is really the natural class. Because you cannot go, look, I mean, how are you going to define this problem here? You're going to take the Dirichlet energy, right? And you're going to minimize that subject as equal to U is equal to phi on the boundary. That's how you solve the Dirichlet problem. You need this one to be in L infinity in order to be able to match it against functions whose gradients are in L2. H1 is a natural space, that's the energy infinity is really the natural space. That's where you could say, is it true that if A and B are isotropic, and you would say, and in L infinity, and of course bounded away from 0, is this true? That's really where the problem should be formulated. And so now we made a very, very precise formula here, and of course elliptics are bounded away from 0. And this is what they proved. They proved that in 2 dimensions for A and B in L infinity and A and B isotropic, then they proved that lambda A is equal to lambda B. The Dirichlet to Neumann data response is the same implies that A is equal to B. This is true. Now, so now you can see the open problem, if there is an open problem, and there is if you are in 3 dimensions and higher, you don't carry it down to L infinity, you only carry it down to around C1 or C2 or C11, some minimal degree of regularity. So there is a space between L infinity, there's a room between L infinity and say C11, where no one knows if lambda A is equal to lambda B implies A is equal to B in those dimensions 3 and higher. Now the reason that you could do it in 2 dimensions, what sort of Astala in a very profound way brought to the table, is the theory of quasi-conformal mappings. And so this operator here, by quasi-conformal mapping, can be taken to the Laplace operator. And so that's actually what sort of was relevant there. But that's very much so the 2-dimensional approach. And so that's why the 2-dimensional thing is. Okay, so now you can see where I'm going to have a terrible problem up here. Because lambda A cannot be equal to lambda 1 if A is isotropic. Basically, I'm going to be in trouble if I believe, so the thing is, well, it doesn't really matter what I believe, but do people believe that in 3 dimensions the same result holds? And actually, the answer is, you may say, well, gee, maybe if it holds in 2 dimensions and it's true for C11, maybe it's also true in 3 dimensions. But sort of the thing that makes it maybe not being quite as obvious that it's true is these results are very much related to unique continuation. Unique continuation results that says when you have a unique solution to the Cauchy problem. And